So we're going to jump into some problems that are going to look super similar to the problems in the previous video. However, we're just going to add a new aspect to them, a new question, which is in regards to the theoretical yield. So the theoretical yield is a best case scenario. And what we're going to start doing is calculating what's known as the percent yield. Basically, you can think about it like a test score. If you expect to get 100 points on your test and you only get 90 points, then you're at a 90%, right? It's something very similar here where what is the best case scenario? Can we get those 100 points? Or what did we actually get? And just so you know, the numbers are going to be a lot lower than what you would want for your test scores. There's a lot of loss that occurs when we actually work in the lab. For instance, whenever we transfer our synthesis, whatever we're making, from one beaker to a filter to another beaker, we wind up losing a lot of material. So some of this loss, the fact that we're getting 80% yield, is beyond our control. Some of it we can control with good lab technique, and other parts it's just part of the process, and we don't expect 100% yield in the lab. That would be nearly impossible. Alrighty, so this first problem is one that you've actually done. So this is when you take that magnesium metal and you burn it in the presence of oxygen gas, and you're told not to look at it directly, right? You have to shield your eyes because of the UV light coming off of that as it burns. And even on this one, I like to ask students, what is the main source of transfer loss? Like, why don't you get 100% magnesium oxide when you burnt that magnesium metal? I mean, we should all know how to burn, a little strip of metal, right? Why can't we get 100%? And so think about that as we're going through the problem, and then we'll come back. I'll let you know what I think the main source of loss of product is on this one. Alrighty, so lots of numbers here. We have 10.1 grams of magnesium. That's one of our reactants. And they told us we have 10.5 grams of oxygen, also reactant. Then they told us we have 11.9 grams of magnesium oxide. That's important information, but we don't need it till we get to the very end of the problem. This is going to be our experimental or actual yield. People call it different things, but this value represents what actually happened in the lab. And so in order to calculate the percent yield, we need to do the same steps that we did last time to calculate theoretical yield. Let's do that. So that involved both reactants. So I'm going to do 10.1 grams of magnesium, and it's just a single component, single element there, so I'm just grabbing the molar mass off the periodic table. Alright, so now that we're in moles of magnesium, we can grab those coefficients from the balanced equation. So I want to get rid of moles of magnesium. Remember, we always have to go to product in these problems. So I'm going to change this to moles of magnesium oxide. And it's a 2-to-2 ratio. Now, since our actual yield was given in grams, I'm going to take this to the level of grams. So now that moles of magnesium is gone, I'm going to use the molar mass of magnesium oxide. So over there I calculated it, 40.31 grams. And it's totally up to you. You could leave it in moles, but having experience with these problems, and a big clue for me is the fact that everything's in grams. I know eventually I'm going to need grams. I might as well just do that step now and get it over with. In terms of what you're plugging into your calculator, you need to do, and let me just write it down. So you're going to do 10.1 times 2 times 40.31. If you want to plug it in all in one step, that's great. That's probably the way to go, but use a big set of parentheses around all the values up there in the numerator. And then you're also going to do another set of parentheses for the denominator. So when I did this earlier, I got, now I'm not going to worry about sig figs too much until the end. I got 16.747 grams of magnesium oxide. Alright, so we're analyzing it in terms of one reactant. Now we have to analyze it in terms of that second reactant. So I'm going to repeat a very similar setup for my oxygen gas. First, I need to turn oxygen into moles. Oxygen is diatomic, so the molar mass is going to be 16 times 2. However, remember with molar mass, you're always going to say 1 mole of blah, blah, blah has blah, blah, blah grams. But it always has to have a 1 if it's molar mass. But I did multiply that 16 by 2. So in the denominator here, I'm going to have 32 grams. Now that I'm out of grams, I can do my mole to mole conversion factor. So I'm trying to get rid of moles of oxygen and convert that to moles of magnesium oxide. That's a 2 to 1 ratio. So the 2 from here, and there's a 1 there that I grabbed. Let me get rid of the moles of magnesium oxide. And since this is a molar mass, I'm going to put 40.31 grams with the 1 mole of magnesium oxide. In my calculator, open up the parentheses, 10.5 times 2 times 40.31. Close the parentheses, hit the divide. There's only one number in the bottom, so I could just do divide by 32. When I did this one, I got 26.453 grams of magnesium oxide. So that allows us to answer several of the questions that we've been asked. So they want the limiting reactant and the theoretical yield. Remember, we're always comparing apples to apples, and we're always going after the smaller of the two values. So this number, gibberish. This is the theoretical yield. So the smaller of the two products will be the theoretical yield. Your theoretical yield is always associated with your limiting reactant. So we know that the solid magnesium then is our limiting reactant. The number that we crossed out, or sometimes there's more than 2 reactants. So sometimes we're crossing out 2 numbers or 3 numbers. So the numbers that are larger that we crossed out are associated with our excess reactants. So oxygen gas is going to be our excess reactant. So I just cleared some space here so we could finish our problem. This is the theoretical yield that we determined earlier. Remember, we're going to take that theoretical yield and figure out how much of the excess reactant did we actually need to make 16.747 grams of the magnesium oxide. So I need to get the magnesium oxide back into moles. So I'm going to grab that 40.31 grams. And I'm using 1 mole of magnesium oxide. So grams of magnesium oxide cancels with grams of magnesium oxide. Now I want to get rid of moles of magnesium oxide. And it needs to go to moles of my excess reactant. So I'm going to do a 1 in front of the oxygen and a 2 in front of the magnesium oxide. And now, since I'm going to have to subtract the values, and this is in grams, I do need to be back in grams with my oxygen gas. So I'll do 1 mole of oxygen, so that this is canceling with this, and it's diatomic, so I know it has 32 grams. I got 6.647 2 grams of oxygen. And when you use your theoretical yield and turn it into your excess reactant, that's going to tell you how much of the excess reactant was used. So my starting amount was 10.5 grams. And we've done this earlier and we were in moles. You can subtract moles and moles and grams and grams. The units have to match exactly though when you do the subtraction. So it's fine. 10.5 grams of oxygen minus 6.6472 grams of oxygen. And there's so many different ways to solve this. I should mention that if you're doing moles minus moles and then converting to grams after you subtract, you're going to get the same answer. So don't worry if you're doing it in a slightly different manner. So 3 sig figs. So I will report that we have 3.85 grams of oxygen gas left over. Because this is how much I had to start, and this is how much we used, and now we have how much is left over. This is one of the values that they asked us for. So the next thing we need to calculate is what is our percent yield. And the formula for that is very similar to any kind of percent formula, whether it be a test or percent by mass composition. We did that earlier in the course. It's the part, and in this case, the part is what actually happened in the lab. So our actual yield or our experimental yield divided by what happened on paper, our best case scenario, which is our theoretical yield. The only units that should remain after we do this problem is the percent. So when we're plugging numbers into this, we need the units to match so that they cancel. So for this particular problem, our actual yield was given in the beginning, so it was 11.9 grams. And it was magnesium oxide. And our theoretical yield, we calculated earlier, was 16.747 grams of magnesium oxide. Again, I can't emphasize this enough. These units have to be the same so they cancel when you're doing this. You could be in moles, absolutely, but moles are the same thing there even. Times 100%. And I just have 3 sig figs, so I'm going to report my percent yield as 71.1%. So again with, oh, that doesn't seem so hot, right? That's like a C if it was a test score. Nobody wants a low C. Think back, hopefully you did this one in lab, you had the opportunity to, when you're actually burning that magnesium metal. You needed to hold on to it. So maybe you used a pair of the metal forceps or tongs, right? You had to have some way of holding that solid magnesium in the hottest part of the flame. So that part, try as you might, never got burnt, right? And so to me, that explains a lot of that 71.1% yield. Maybe about 30% of the metal or so is the piece that we're holding on to. Alrighty, so yes, we're still working on yields. However, part A of this next problem has us writing a balanced equation from a description. So it says when heated elemental lithium, so just lithium by itself, most of our metals are solids at room temperature and also just monoatomic. Lithium reacts with nitrogen gas. So nitrogen gas, that's a diatomic gas, to form solid lithium nitride. So here we got to do a little bit of work. It's an ionic compound, so we're going to crisscross the charges. So lithium is a group 1, so I'm going to do a +1 for that. Nitrogen is group 5, so I'm going to do a -3 on that. And then when I crisscross them, I get Li3 and 1. They told us that it's a solid, so we'll do that there. Then we have to balance it. So the first thing that sticks out to me that I have 2 nitrogens. I can't really do anything about that. They're going to come in groups of 2. So this, well, I could put a 2 out front here, and that would give me 2 nitrogens. At that point, I have 6 lithiums, which I can fix there. So we're going to have 6, 1, and 2 as our coefficients of that balanced equation. The other thing that I wanted to quickly discuss before we move on to the calculations would be what kind of reaction is this, right? So we have 2 things coming together. So we can call this a combination reaction or a synthesis reaction. Secondly, these elemental things have oxidation numbers of 0. Here we have a +1 on the lithium and a -3 on my nitrogen in terms of oxidation numbers. So we see lithium loses electrons. It went from 0 to +1. Nitrogen gains electrons. We have a gainer, we have a loser. So this is also a redox reaction. So the second part of this problem asks to calculate the theoretical yield of the product, the lithium nitride, and they give us the grams of both of our reactants. So I'm going to start with the 12.3 grams of lithium. I need to turn that into moles. So I'm going to grab the mass from the periodic table. Now that I'm in moles, I can use my mole to mole ratio. So 6 moles of lithium produce 2 moles of lithium nitride. And they did ask us to have our theoretical yield in grams. So I'm going to put the molar mass of lithium nitride as my last conversion factor so that my answer is in grams. So I'm going to grab that. I already calculated it. It was 34.833 grams. And again, I'm using the 1 mole with my molar mass. So for that one, I got 20.5756 grams of the lithium nitride. And now I have to repeat with the nitrogen gas. Remember, we always have to analyze both reactants. So I'm going to do 33.6 grams of N2. It's diatomic, so I'm going to put 28.02 grams of N2 in the denominator. Also, again, to remind you all, I don't worry about the coefficients when I'm calculating the molar mass. So that's why, for instance, with lithium, I just used 6.941. I didn't worry about this 6. The coefficients are captured in the mole to mole ratio. So we don't want to capture them twice. So this one is the coefficient, and then we have 2 moles of lithium nitride. And then I'll tack on the molar mass of lithium nitride. So when I did that calculation, I got a much larger number. So 83.5309, just keeping extra sig figs. Therefore, that number is meaningless. We'll never make that much of the product. And so through this work, we've successfully calculated our theoretical yield. We're also able to, they didn't ask us, but we can identify our limiting reactant, which is the lithium, and the nitrogen gas would be our excess reactant. At this point, we've done a lot of problems where we answered that perennial question, how much of the excess reactant is left over after the reaction is complete? They didn't ask us that in this question, so we don't even need to go there. The next part of the question asks us to figure out what is our percent yield. So if everything went perfectly, we should have been able to calculate about 20.5 grams of lithium nitride or so. But in reality, we only got 5.89 grams. So it's going to be your actual amount that was produced divided by the theoretical amount that could have been produced if everything went 100% perfectly. They're both in grams, so those units are going to cancel. And then the only units I'm going to have left would be due to the percent. So their percent yield was about 28.6% lithium nitride. Alrighty, so the first thing that I want to talk about with this problem are the molar masses. So remember, you do not need the coefficients of the balance equations to calculate the molar masses. So here we have 8 sulfurs. And on my periodic table, sulfur has a mass of 32.066 grams. Your periodic table might have a different value, as well as the one in ALEX. When you're doing your ALEX homework, make sure you're using their periodic table. But at the end of the day, we should more or less get the same values, like the percent yield and all that. So I'm going to take that mass of 1 sulfur and multiply it by 8. When I did that, I got a molar mass of 256.528 grams per mole. So that's the value that I'm going to be using for S8. We have diatomic chlorine, so I'm going to do 2 chlorines. Each one of them individually is 35.45 grams. So I need to multiply that by 2, and I get 70.90 grams per mole for the chlorine gas. And then the last one, S2Cl2. So I'm going to do 2 of those sulfurs, 32.066 grams times 2, and then 2 of the chlorines. So 35.45 grams times 2. I multiply first, and then I add those up for a molar mass of 135.032 grams for the disulfide dichloride. At this point, let me balance the equation. I notice that there's an 8 here, so I'm going to fix that first by putting a 4 here. So now I have 4 times 2, I got 8 sulfurs. 4 times 2, I got 8 chlorines. So if I put a 4 here, now 4 times 2 gives me the 8 chlorines. So now it's balanced, and I can start my analysis of the reactants. Alright, so starting with the 4.06 grams of the S8, and I need to get that to moles. So I'm going to grab the molar mass that I just calculated. So the 256.528 grams of S8, and I'm going to use that with 1. We're out of grams. Now we're into moles. Trying to get rid of moles of S8. And there's only one product, so I'm going to pick the disulfide dichloride. And then I throw my coefficients of the balance equation in there. Since the actual yield was given in grams, and I needed my units to match when I do that calculation, I'm going to take this one step further and convert it back to grams. So 1 mole of S2Cl2, that has 135.032 grams. So my units are going to be the grams of disulfide dichloride. And again, I'm not too worried about sig figs. I'm just keeping a bunch till I need to report my final answers. So that's my first potential product value. Now I'm going to grab the quantity of the second reactant. The diatomic chlorine came at 70.90 grams, and that's for 1 mole of that. Now I need to get rid of moles of chlorine. There's a 4, and there's a 4 with the product. And then I'm going to use the molar mass of the product. And I got 11.884 grams of disulfide dichloride. So I'm going to cross that one out. It doesn't apply here. I have 3 sig figs. So if my problem were done, or when I calculate my theoretical yield, I'm going to say it's 8.55 grams of S2Cl2. However, moving on to my percent yield part, I'm going to use the larger numbers. So they told us in actuality, the chemist only made 6.55 grams of the product. But we just determined that they could have made 8.54846 grams of product if everything went perfectly. So again, 3 sig figs, and so I'm getting a percent yield of 76.6% for this particular reaction.